So I'll go through basically just an introduction to FEA, and I'll show you some examples that are more focused on basically vehicle FEA examples, I've called it here. So some of them will be sort of very specific, and hopefully some of them will sort of excite you and sort of show you some of the things that are possible with answers with application to Formula SAE. Okay, oops, this should be, what are you seeing there? Sorry. Okay, so why is simulation important? So here, these are a few animations that I've just sort of picked out from sort of applications for basically vehicles. So if you look at some of these scenarios here, if you did this with physical prototyping, it'd be quite a time-consuming and expensive process. So here, this is basically a car crashing into a lamppost. So here we're looking at the lamppost itself. We don't want it to damage the car too much and kill the occupants. So obviously we don't want to crash too many cars into this thing because it can be quite an expensive process. So we do all of this on a virtual model, and then we do a final physical test. So you can see that those two things correlate quite well. You've got the real thing and then the simulation. So you can be quite confident in your virtual design before you actually commit it to being used. So we've got a roadside barrier here with a car crashing into it. So these tests again are quite expensive to undertake. So a lot of this stuff is designed in a virtual environment. And then we've got an occupant being, a pedestrian being hit by a car. So this is more designing the bumper bar and crash structure of the car to not cause too much damage to the pedestrian. Okay, so obviously these things would be dangerous to do on a real person. So they use crash test dummies for this sort of thing, and these are instrumented with accelerometers and the like. So you can correlate what happens in a physical test to what happens on a virtual model. Okay, so I'm sure a lot of you have heard the term finite element analysis. So what is it? So I'm sure you're all familiar with this equation of motion. So you've got static terms, kinetic terms, and inertia terms. So you can solve this for a single particle, but we want to solve it for a whole system or a very complex model. Okay, so this is just another crash test. So we numerically solve this equation for every point on this particular model. Okay, so sometimes we don't have inertia terms. So in this case, it's we've got a metal forming operation, so it's happening quite slowly. So we don't have any inertia terms. So our equation reduces. So we've got less terms in there. Okay, so for most systems, we're looking at static behaviour. So we don't have any acceleration or any velocity, so we just have F equals kx. So easiest way to sort of build this up to a finite element model is if we look at a simple system of just a spring. So the spring has a stiffness that we know or we can calculate. So if you apply a force, it will have a deflection. If you double that force, the deflection will double. So this is linear behaviour. Okay, so you can solve this just with a single equation. Okay, if we have two springs in series, we now have two unknowns, two displacements, but we know the two stiffnesses, so we should be able to calculate those two displacements with a set of simultaneous equations. So you can use matrix methods to do that. So if we, instead of treating these as one-dimensional springs, we turn these into elements. So instead of it being a single stiffness value, it might be a multi-dimensional stiffness, or we call it a stiffness matrix. Okay, so now we're calculating the displacements at these two elements. Okay, so if we look at a more complicated solid, So what we do is we take that solid and divide it into elements. So at each one of these elements, it's very easy to calculate the behaviour at the nodes or the points that those elements interconnect. So based on that behaviour of each individual element, we build that up until we get the behaviour of the entire structure. So now instead of us having an equation with, say, a 2 by 2 matrix, we have a matrix that can be n by n, where n is the number of degrees of freedom of the model. So the models are built up of these individual building blocks called elements. So here we've got a 10-node tetrahedron, and here we've got an 8 or 20-node brick element, depending on whether it's high order or low order. So if you have a model with, say, just one element, let's say, then you've got 10 times 3, so 30 by 30. You've got a 30 by 30 matrix. So if you think of this as a much larger model in terms of how big the model becomes, so here we've got 3,500 elements, nearly 16,000 nodes, and just under 47,500 degrees of freedom. So if you try and solve this by hand, you'll be there for quite a long time. So 10 by 10 equations, maybe you can solve that fairly easily, but for much larger models, so this is why FEA was invented. So you can solve quite large problems. So when I first started using the software, probably 1.7 million degrees of freedom was about as much as you could solve on a 32-bit machine. But now there's pretty much no limit to what you can solve because you've got access to very high-performance computers. So today a 1.7 million degree of freedom problem you can probably solve in 5 minutes. So first time I attempted a model that big, it took probably 5 or 6 hours. And if it was non-linear, you're talking about maybe a day and a half to solve. So those days are gone. A 1.5 day model, you guys probably wouldn't see a model like that. Okay, so in terms of the types of finite elements that you can use, so if you've got a very complicated shape like this fan blade, or it's basically a pump impeller, so it's quite a complicated shape. So you need to represent it as it is, as a 3D solid. So all of the geometry is kept and represented. So something like this. So this is basically just a car body. So it's very thin structure. So it's thin plates. So you can represent that with 2D shells, where you numerically model the thickness. So if you were to model this with solids, it'd be a much more complicated model. So here we've got a 1D model. So we call it 1D because it's just a line, and you assign the cross-section property to it. So something like a space frame chassis you could represent as a 1D model. If you're just looking at the overall stiffness behaviour, not so much the stresses at the joints, you can get away with a 1D approach. So if you compared the number of nodes you'd need to do a 1D model versus doing it as a 3D, you're talking about maybe a couple of hundred nodes here to maybe a few million if you did it as solids. So the solve time difference between those two is quite significant. Okay, so for some structures you get non-linear behaviour. So this red line here is basically an unknown path. So until you solve that incrementally, that's the only way you build up that, where you can find out what that stiffness is. So if you think of a non-linear spring, as you stretch it, its stiffness will change depending on how much displacement you apply to it. So here, if you think of this as your structure distorts, its stiffness will change. So that can be based on a number of different factors. Okay, so it can be because of your geometry. So if your geometry changes shape, the stiffness of your structure can change. So if you think of a fishing line, so it's very flexible, So you calculate its stiffness based on its initial geometry. When that geometry deflects, it's going to have a different stiffness because its shape has changed quite significantly. So you can also have material non-linearities. So this isn't only when you've got metal plasticity or materials yielding. It can also be rubber materials where you've got quite large strains. So normally in sort of small strain regions of say 0.2%, you can use your initial length to calculate your strain. But once you get strains above a couple of percent, you can't use that approach anymore. You need to incrementally calculate your strain. So the third one is contact nonlinearities. So when I say contact, when bodies interact, different areas might be in contact, and that will change your load paths and your characteristic stiffness. Okay, so here this animation shows all three nonlinearities at once. So you've got large deflection because you've got a large amount of shape change. You've got quite significant strains. So this is a rubber boot, so there's quite a lot of stretching going on. And you've got contact happening as well. So this part's coming into contact with itself. So that's changing the load path. So that's going to create a stiffening response as more of these bellows come into compression. So if you think of a one-dimensional spring, if you compress it enough, the coils will collide, and that's going to change the stiffness to be basically based off the material rather than it being based off the coils. Okay, so when we have an FE analysis, we follow a very specific workflow. So I'll sort of go through these steps, excuse me, to sort of explain the sorts of typical things that you would do. So the first thing is to plan your analysis. What sort of analysis do you need to do? Is it just going to be a static analysis? Does it need to be a dynamic analysis? So is there inertia effects present? Do you want to find natural frequencies? So then you need to decide what sorts of results you want to look at. Do you want to look at maximum deflection? So if it's just your say your suspension arms, you want to see how much they deflect under load, or do you want to find the stresses in your structure? So that will sort of determine what sort of modelling you need to do. So do you need to account for non-linear effects? So this is one of the ones that a lot of people sometimes skip over. They think because it's sort of small deflections and because it's a linear elastic, there won't be non-linear effects present. That's not always the case. How quickly do you need your results? So if you're after just a quick and dirty, that's probably the wrong word. If you're after just a quick result, so if it's just a static deflection of your chassis, you can get away with beams. If you're wanting to look at stresses at all of your joints, then you probably can't get away with beams. You might need to use, say, a sub-modelling approach, which you'll learn in one of the workshops. Or if it's just the crash attenuator on the front, you don't need to model the whole chassis to do that. You can just model the crash attenuator and just a little bit at the back that sort of holds the attenuator in place. Okay, so is FEA an appropriate tool? Maybe not. You might be able to get away with hand calcs. If it's just a static deflection under load, you want to see how much your springs compress. FEA is probably overkill for something like that. Okay, so this is just a slide to sort of show explicit dynamics. So this is a different solution approach. So a lot of the things you would have learnt so far are probably using an implicit method where you solve the equation of motion. With an explicit simulation, it's a totally different solution process. So it's usually reserved for very high-speed impacts, highly non-linear behaviour in materials. So you're talking about very high strain rates. So usually what dictates it is if you've got significant inertia forces. So there is some sort of overlap. So something like metal forming, you can do as either an explicit or an implicit. So for a crash simulation, so you may be able to get away with an implicit simulation there, but if it's highly non-linear, you probably need something like an explicit simulation. Okay, so the second step is geometry. So most of the time you'll have some sort of CAD geometry there already. So it's just reusing that geometry for simulation. So here we've got a CAD model of an engine. So if we're just interested in the kinematics, say how much force it takes to make this piston go through its stroke, you don't need to include the cylinder bore. You can just include joints or contacts to simulate the interactions with parts that you're excluding. So here this cylinder bore is just for visualisation, so because it wouldn't really look very pretty if you've just got a piston floating in space. And here we've just got stresses showing on the crankshaft. So you can sort of use a mixture of rigid and flexible bodies. So if you're interested in just some parts of the structure, this simplifies your analysis quite significantly. Okay, so the third step is your setup. So material properties. So normally they'll be fairly standard material properties. So ANSYS has got inbuilt libraries for those materials. And then the loads and supports, you can usually just use something fairly, or they'll sort of fall into any one of these sort of categories. So you probably won't have very complicated support conditions that won't be covered by the standard conditions that are available inside the software. Okay, so meshing is probably the, I suppose, one of the more intricate things you need to deal with. So you probably would have already decided whether or not you're going to use shells or solids. So here we've got a part of a car chassis that's modelled as shells. So you can see it's sort of representing the thickness when you display the mesh. So the thickness will be a property assigned to the surfaces, and then when you mesh it, the mesh will inherit those thicknesses. So here this is probably an aluminium or magnesium wheel rim, and it's got quite a nice structured mesh on there. So don't be too drawn in by having to have a nice, pretty looking mesh. So here we've got what we call a hex mesh. So it's basically composed of sort of fairly nice uniform brick elements, and here we've got a TET mesh. So hex mesh requires a little bit of extra effort sometimes to achieve. TET mesh, really there's not much extra effort apart from just assigning a sizing. So these two meshes will give exactly the same results. So sometimes it's not worth investing extra time to get a hex mesh, especially if you're after very quick results as well. Okay, so probably one of the most common questions people ask: how do I tell how good my mesh is? Well, there's some checks or metrics that you can look at for your mesh. So it's not going to be excellent everywhere. If you try to achieve these excellent metrics everywhere, you probably spend days meshing. So you really need to get the, or I suppose the metrics very good in areas of interest. So if you've got an entire model, it might only be part of the structure you're really interested in. So you make extra effort to get the mesh good in that particular area. Okay, so the fifth step is the solution. So what sort of solver are you going to use? Do you need to use parallel solve or distributed? So if you use distributed, you might be using multiple CPUs to try and get the solution to solve quicker. So by default, the software will solve on 2 CPUs. So if you've got a multi-core machine, running it distributed can help speed up that solution. So if you're after results really, really quickly, just use more CPUs in your distributed solution. Okay, so once you've got a solution, you would review your results. So this is just a static image, but if you animated it, you'd make sure your deflections were going in the correct directions. So usually you have some sort of idea of what your results will look like. So you've got to be very careful with how you interpret your results as well. So it's very easy to get believable results and the results are incorrect. So one of the first things you would do, check your reactions. Do they balance your applied loads? If you've got gravity applied, is your structure deflecting in the correct direction? So here this is an example of a rubber seal sort of going through an opening. So if you looked at the reaction force, you would sort of expect there to be a large a drop-off as this seal pops through the gap there. And then when the two parts come into contact, you would expect there to be a different sort of stiffness, because there's a different sort of mechanism for the load transfer there. So these are sorts of things you can quite easily check. So as the seal's going through, it's friction dominated, and then once the seal pops through and the two parts are in contact, it's dominated by the material properties. Okay, so after you've made your first pass of a solution, you might need to do a second pass. So usually for more complicated models, you go through an iterative process. So you start simple and then you increase the complexity. So here we might find that we've got very high stresses at this sharp corner. So you might sort of have a look at the stress gradients. If they're quite high, it might mean you need to refine your mesh. So when you refine the mesh, it's going to take longer to solve. But this might be the only area in a very, very large model that requires that refinement. So you wouldn't put this fine mesh everywhere because it's going to take longer to solve. So doing this sort of multi-step approach, you sort of reduce your overall solve time. So don't be tempted to throw all of the complexity into the model at once, because it's much harder to debug a model with all of the complexity in there than sort of finding these problems along the way. So if you're debugging a linear model, it's much easier. So although you're getting incorrect results, you're getting the incorrect results very quickly rather than waiting, say, maybe minutes in this case, and maybe tens of minutes here. So that's usually the best approach to take. Okay, so here this is basically, it's meant to be an animation of a train crashing and falling over. So FEA is just like any other tools that you use. The beam equation is an engineer's tool. FEA is the same sort of thing, just it's a bit more complicated. So it's a tool that's very easy to misuse. So the term we always like to use is garbage in, garbage out. If you put in the wrong inputs, you're going to get the wrong outputs. So you've got to make sure your approximations are meaningful. So in some cases you might exclude parts of a structure. So here in this case we've used rigid bodies at the back because we're not interested in how they, what sort of happens to those as they hit the embankment. So in this particular case, these carriages were undamaged, so we didn't need to know what the damage was. So no need to include that complexity. So a lot of people think that FEA is a black box. It's not. So the equations that it's solving under the hood are very easy to understand. So there's oftentimes very easy checks you can do to your results. Just to get a sense of whether or not the results that are coming out are meaningful. Okay, so now for some sort of vehicle examples, so some different FEA applications. Okay, so brakes. So I'm sure a lot of you are probably going to be doing FEA on the brakes of your cars. So you can look at things like the temperatures of the discs. So if you're machining them to make them thinner, you obviously want to ensure that the thermal performance isn't degraded. You don't want to overheat your brakes because then they'll stop. They won't work as well. So you can look at how the brake interacts with the upright. So you can sort of maybe estimate the loads or include the brake disc and apply some sort of loading on there to see how that load gets distributed through the rest of the suspension system. Okay, so you can include CFD in this as well to sort of look at the cooling of the brakes. Okay, so you can do things like predicting brake squeal. So in a race car, that's not so much of an issue. So usually that's an indication that the brakes are working. But on say a passenger vehicle, it might be something that someone in, say, a very high-end car doesn't like to hear. So you can use FEA to sort of simulate that as well. So the brake squeal is basically induced from vibration, so it's sort of frictional slip, and it's sort of almost like a chattering. So you can simulate that quite easily. Okay, so you can look at things like brake wear. So you can, as the brake pads wear, the pressure distribution will become more even across the pad face. So this is the sort of things you can simulate as well. Okay, so you can look at things like kinematics. So here this is an entire engine assembly. That one doesn't play. So you can look at things like the out of balance forces as the engine's rotating, or it could just be your suspension movements. You want to see how the suspension travels as it rides over bumps, or you might sort of see if your spring rates are fairly linear, or you've got any non-linearity built into your linkages. You can quickly see how that behaves. So something like this engine. So all of the joints are detected automatically as you bring the model in from CAD. So you might need to fine-tune some of the behaviours of those joints, but it's very easy to set up your mechanism behaviours. And you can also model some of these bodies as flexible and some of them as rigid. So if you had, say, an entire suspension or one corner, you might want to look at the upright as being flexible and the rest of the structure as being rigid, just to simulate the load paths. Okay, so here this is two more animations that aren't playing. Okay, so just sort of some other sort of examples. So if you look at, say, so this is just a chassis subsystem. So it might be, say, your rear suspension. So you want to look at the overall stresses of the entire suspension system as it, say, rides over a bump. So this will have all of the joints built in there, and it might also have contacts. So when you look at how bodies interact, you can do it with either joints or with contacts. So joints are probably easier to generalise. So you might have, say, a spherical joint or a revolute joint. So they're very easy to set up, and they're simpler than doing it with contact. It's not to say that contact isn't an approach you can use. It's just that the joints make it simpler to set up and sometimes easier to solve. So if you want to sort of focus on a particular area here, so this is an upright near one of the joints, so you can sort of look at localised stresses. So this, in this case, this might be the flexible component, and everything else is rigid. Okay, so please let this animation play. All right, so this is basically a space frame. So it's everything is rigid except the tyres, and we're exciting the car by having it ride over bumps. So here you can see it's quite extreme. The wheels are leaving the ground. So obviously the car is not going to be able to slow down or speed up with the wheels off the ground. So if you're looking at trying to see the effect of, say, spring rates or damper rates, or maybe even the bell crank, if it's got any non-linearity built into it, if you want to quickly see how that will change. So if this is the car in, say, the early design phase, you don't want to be changing things like bell cranks when the car's already been built, and you find out that as you're testing, you go over a bump, the car's off the ground, and then you're in the barrier. That's not what you want to have happen. So you can extend the complexity of this model. So this is basically almost like a 4-post rig. So you can have motion with this as well. So I've got a very, very simplified model of just a box with wheels on it and applying some steering, and you get this sort of dynamic behaviour going on. So there's no reason why you couldn't do this with this car and then put things in like tyre slip angle behaviour to get a very complicated dynamic model. So the sorts of things you can get out from this model, so this is the vehicle response, so it's the vertical acceleration, and then these are basically the 4 bump inputs. So they're sort of out of phase to try and sort of see the behaviour of the car as it rides over road irregularities. And these are the 4 spring compressions. So the springs have got both stiffness and damping, so you can change those values to see the behaviour of the car. So you might want to get these spring deflections down to try and keep the car on the ground. Okay, so if you wanted to look at, say, the forces at the bell crank, so if you're wanting to size the attachments to the chassis, so if this was a carbon fibre tub, you don't want to have the bell crank pivot sort of ripping out of the structure. So you need some sort of idea of what forces are going to be transmitted there to size the structure, and also maybe the layup around that area. Okay, so here this is that same model. So here it's quartering, braking, and acceleration. So I'm not sure if it leaves the ground in this instance. So you can sort of see the attitude of the chassis as it's sort of going through those motions. Okay, so this model is available if anyone wants to use it as, say, a starting point. So as I said before, it's just the tyres that are flexible here. So, and they've got internal pressure in there as well. So that's the extent of the realism of this particular model. Okay, so here this is another sort of chassis example. So this is just riding over bumps. So the contours are basically the stresses in that frame, and it's got all of the articulations and all of the joints and the suspension springs in there as well. So this is some sort of vehicle. I'm not exactly sure what it is. It's some sort of I think it's either a bus or a truck. Okay, so here this is this one there. So it's basically a suspension from, I think it's a NASCAR. So it's quite rudimentary. So you can see the upper and lower A-arms are modelled as flexible. So you've got the contours of the stress as it's sort of riding over a bump and steering. So the other parts there are modelled as rigid bodies. So that's just to provide the load path for the loads in the structure. Okay, so there's a few, I guess, best practices you should follow. So you should always have a clear objective of what you want to achieve with your simulation. So it's going to drive things like what sort of elements you use, whether you use a CAD model or whether you just create something from scratch in Design Modeler. And whether you de-feature as well. So in terms of setting expectations for your customer, so the customer is normally yourself, or someone else in the race team. So the important thing to remember is there's always some sort of trade-off. So it's usually how long it's going to take you to solve versus accuracy. So there'll be a point where you throw more elements at a model, you're not going to get your results to be any more accurate. So as you start doing more simulations, you'll be able to determine where that point is. So when you're sort of doing your first few simulations, you might need to do some sort of mesh sensitivity study to see when your stresses stop changing. So that usually takes a little bit of practice. So you can always lean on us to say, hey, does my mesh look right for what I'm trying to do? We're more than happy to answer those sorts of questions. Okay, so defeaturing a model, and one of the ones that a lot of people overlook is the use of symmetry. So try and use symmetry whenever you can, because it means you can throw more elements at half of the model or a quarter of the model, rather than having a coarser mesh on your entire structure. So you've just got to make sure that your structure and your loadings are symmetric before you do that. So I would always start with a very coarse model, just to see that your model is behaving as you expect. So the important thing that a lot of people often forget, you should always try and verify your results. So that doesn't mean you have to go and do a physical test for every simulation that you do, but things like checking your reactions, don't just hit the solve button, have a look at your results, nice pretty pictures, that looks right, must be right. Always do these checks and balances. Okay, so when you go out into the workforce, you'll be expected to have a basic understanding of how these tools work. So you might be checking other people's results who are using simulation tools. So if you're getting someone else to do simulations for you, you need to have an understanding of the results that they give you. So a lot of people fall into the trap of relying heavily on the person who does the FEA, and then they just accept the results that they're given. You should always be vigilant in checking your results. So don't just trust what you get out. Always check. Okay, so there's benefits and risks with doing simulations. So like I said, whenever you're doing sort of more advanced things, so if you're doing, say, a crash test in a simulation, you would always do some sort of final physical test to see that your FEA results are giving you what you expect. So it will give you more trust in future simulations that you do. Okay, so don't be scared off by FEA. So learn to use it, and then learn to understand the results, and then you won't be so intimidated by it. Okay, so this is just a little checklist. So gravity pushes downwards, spinning objects move radially outwards, heated objects grow. You don't see stresses of tens of thousands of megapascals. So if you see that on a model, start looking at things like, start looking at things like your material properties, or if it's a stress singularity. So bending loads, so I mean you understand that one side's got compression, one side's got tension, so it's very easy to check those sorts of things. Okay, so that's the end of my presentation. So